Hello, my name is Viva Conniff. I'm the CEO of Reduction Tech and also the founder. And today I'm going to talk about the features of our lower energy oxide dye radical that we generate from our ceramic membrane. So there are two oxygens that I'm going to talk about. One is the O1D ozone atom, which is found in the atmosphere. It is created at the level of the ozone layer and other levels in the troposphere, and it comes from the photodissociation of ozone by solar UV radiation at wavelengths less than 310 nanometers. By comparison, the oxide radical or dye radical is created with infrared radiation, which has wavelengths between 780 nanometers and 1 millimeter. So we can actually calculate the precise energy difference using the Boltzmann constant, E equals HR, which I do here on this page, calculating the difference between the energy level of an O1D ozone atom and our oxide dye radical. So we plug in the Boltzmann constant for each one of these with their energy levels, and you can see that the energy difference works out to 4.26 times 10 to the minus 19th joules. So the O1D ozone atom has precisely 2.5 times the energy of an oxide dye radical. The radical will then create lower energy hydroxyl radicals, which we consistently produce when we sparge that gas flow of the oxide radical into water. The pH probe typically would raise within a couple of minutes up to a pH of 10, sometimes going to a pH of 11. This is important because the lower energy hydroxyl radicals will stabilize with time to hydroxide ions. The hydroxide ion is the stable form of the hydroxyl radical. The hydroxyl radical has an electron associated with its orbit that is not stable, but over time it stabilizes, and then we call it the hydroxide ion. So this means in the atmosphere, when we propose to release it, that over time during a daylight release of hydroxyl radicals, that overnight the hydroxide ion will be present because the cooling of the environment will stabilize it to the hydroxide ion. The structure of the oxide dye radical is like this, the Lewis dot structure. The stars indicate the associated unstable electrons of the oxide dye radical in its orbit. The oxide radical from our emitter is inside the emitter. It is a ground state oxygen atom which is exposed to heat and catalysis. And as it moves across the ceramic membrane, it is stripped of 2 of its own electrons, and they are reassociated to the atom, but they are now unstable in their orbits. When the oxide contacts water and has a nucleophilic attack reaction on it, doublet hydroxyl is formed, and it contains 20% of the energy of a photolytically formed hydroxyl in nature. Here are 4 of our early prototypes. This one received oxygen across the ceramic membrane and generated lots of sparged hydroxyl and high pH solutions. This one did the same thing as well too. It was a little bit larger. This is a unit that would be basically a technology readiness level of 9, and it was designed to create doubly ionized oxygen, where the electrons that are stripped from the oxide radical were taken to ground, so that the oxygen that was produced was actually doubly ionized oxygen, which was successful. This is the Industrial Research Assistance Program unit that we had up and running at the Domtar Pulp Mill in Kamloops in 2010. And we had a consistent high pH solution produced from this first concept test unit. And we had it verified that it was producing a high pH solution that was stable for several days in a row in water. This is Ray Woodley. He signed off on numerous runs to that effect. So this is a photo of our pH probe with a pH of 10.01. Again, that was a consistent pH reading. So on to our CO2 crusher. This operated for 3 years. It was at a technology readiness level of 9. It produced from CO2 tetrahedrally amorphous diamond-like carbon powder and oxide, the diradicals from the ceramic again. And they also produced high pH solution as well consistently. Every time it was run, it was checked and recorded and documented. The system is currently in storage. At the time in 2012, I also connected a bottle of air to it and produced oxide radicals from air, which concept proved the fact that we can process air in these systems as well. For the CO2 work in 2012, we were nominated for a Nobel Chemistry Prize by Dr. Finn Nordmo. This vessel will also scale up in size and output. Catalysts keep the oxygen from recombining to O2. Okay, so I'm going to explain that so that there's very little room for misunderstanding. Inside this ceramic pipe, the heat and the catalytic effect of both a heterogeneous catalyst and the yttriadope zirconia itself causes the dioxygen to form atomic oxygen, and when pressure is applied, that atomic oxygen will pass across the ceramic wall. So only a small amount of pressure is required to do that for the feed gases of oxygen, CO2, or air. Here's the geometry of the yttria and the zirconia, showing the well understood oxygen vacancies that are happening. Here is a diagram showing that the O-2 is going through the ceramic in A and B, and the electrons relocate to the outer surface of the ceramic, and typically there is a charge, an added electrical charge, where other techniques bathe that oxide radical in electrons, which give it enough energy to reform back into O2, because the recombination coefficient requires that it has some energy supplied to it to accomplish that. Because of the catalyst that is present in our system in that specific area, the catalyst prevents the reformation of O2. Okay, so the two electrons in the unstable orbit create the diradical. And that's what we get from our system. Our next system that we want to have done for the Canadian Standards Association is a ytria pipe with a heater inside it, a thermocouple, an air supply on one end, a nitrogen exit on the other, and then an oxygen diradical exit on the side. It's a very simple unit. It only has 55 parts. It's low tech. It's highly scalable for providing this oxidation remediation for atmospheric mitigation. And all we have to do for that is repeat the technology, line them up, and do numerous numbers of them, and they will scale up. This 40-centimeter pipe is capable of generating 2 tons a year of oxide radical to the atmosphere, which we know from our relative abundance apportionment calculation and teachings, which are available online, that the carbon removal is highly cost effective and scales to $50 a CO2 equivalent. So here's a reference that I'll just cite for this. And I'm going to conclude there because we just wanted to focus on what was happening with our diradical and make sure that the understanding of that is more clarified. Thank you very much for your time.